Hello, this is the next video in a playlist that I'm calling General Linear Models Design of Experiments. And this is part 11 of an 11-part mini-series within that playlist. Here we're looking at hierarchical designs, and we're going to cover a nested and crossed design. And we're going to use data from Montgomery. It's example 13.2, table 13.8, and it deals with the time needed to assemble electronic components. And so they're exploring the idea of assembling these parts by hand. And so they wanted to test that. So they have three different fixtures, and I'm not 100% sure what that means. And they have two different layouts. And so those two levels are crossed, fixture and layouts. Now within a layout, there's two different layouts, two levels. In level 1, they're going to use 4 operators to assemble parts, and then in level 2, they're going to assemble another 4 operators. So it's 8 operators total. So operator is nested within layout. Fixture and layout are crossed. Operator is nested. So let's load the data and look at this. So we have the time, the fixture 1, 2, 3. We have layout 1, 2, and operator 1, 2, 3, 4 within layout. Reps is 2 because each one is done twice. Now we use operator 1, 2, 3, 4, and then within layout 2, 1, 2, 3, 4. But technically we could call it 1, 2, 3, 4, 5, 6, 7, 8 because they're 8 unique operators. But notationally we usually just call it 1 through 4 and then 1 through 4 again. Now let's set up the design matrix. So A is 3, B is 2, C is 4, there's 4 operators, and N is 2, there's 2 replicates. We put the response time in Y, and then we create empty column matrices here associated with each of the parts of the design. We have factor A, factor B, and the interaction of factor A and B, because they're crossed, we have factor C, which is operator, but we're also going to look at the interaction between A and C. So fixture and operator can be crossed, but C is nested within factor B. And so then these statements here put in the correct ones and zeros everywhere. And then this is the design matrix. So it's quite big. So first column deals with the mu parameter. Next 3 deal with factor A. Next 2 with factor B. Next 4 with factor A, and then so on. Then we have the interaction space, and that's it. So here in part 2, we set up the perpendicular projection matrices onto each of these little column spaces. So we have J associated with the 1 vector, MA, which is the perpendicular projection matrix on the column space of XA, MB, M dot AB, MC, MAC, and then just M, where M is just the overall perpendicular projection matrix onto the whole column space. Now we're going to set up the ANOVA model in R and then show how to calculate it by hand using these matrix manipulations. I want to expand this just so we can see this. So here, fixture and layout are crossed. So fixture star layout, that means we're going to have an effect for fixture, an effect for layout, and the interaction term for those. And now here, then it's plus, and we have an interaction between fixture and operator, but operator is nested within layout. So this is how notationally you write it. Okay, so let's, and then I want to have it just enough. Okay, so now if we already ran it, so now let's look at the summary. And here it is. So we have fixture, layout, interaction between fixture and layout. We have operator within layout, and then we have fixture and operator, but operators within layout, and we have the residuals. And then we have sum squares, degrees of freedom, mean square, the F value, and the P value. So now let's start calculating those. So the sum of squares for factor A is y transpose MA minus JY. And notice we get 82.79 if using the matrix calculation. So degrees of freedom is the rank of that matrix, which is 2. And each time I'm going to resubmit the summary, so it's always present. So then the sum of squares for factor B, which is layout, is y transpose MB minus JY. And we get 4.08. It's the same. Degrees of freedom, 1. The summary, that's the assembly. That's now we're going to do the sum of squares for the interaction between fixture and layout, which is, y transpose M dot AB minus MA minus MB plus J. And notice we get 19.04, the exact same as what R produced. The degrees of freedom was 2. Now, when we look at the sums of squares for operator, it is y transpose MC minus MB. And all this is derived in the video that we did. I think it's part 9. And we get 71.9, and it's the same as what R produces up there. It's the operator within layout. Degrees of freedom is 6. Now this next one is it's the fixture operator interaction, but operator is nested within layout. And so there's the sum of squares if we were to calculate it by hand, 65.83. That's the same. Degrees of freedom, the rank of that matrix in the middle of the quadratic form, 12. The sum squares there is always, y transpose I minus M, y. And so that's 56. And then the rank that's 24. Sum of squares total, that's if we add up all of those sums of squares, and we get 299.666. And then if we were to use it in, calculate it in matrix form, this is total, 299.67. Degrees of freedom is 47. Now the mean squared error is the sums of squares divided by the degrees of freedom. So it's kind of a no-brainer. So here we get 41.395, which rounds to 41.4. There's the mean square for B. And I'm just showing you that what we do is equal to what is done in R. So there is the mean square for the interaction term, which is 9.52. Mean square for operator, which is 11.99. And here is the interaction between fixture and operator, but operator is nested within layout, and that's 5.49. Mean squared error is 2.33. Now the F test is the ratio of those mean squared errors. So the test statistic for fixture is 17.74. Factor B, 1.75. And notice these, I'm probably going a little fast so you can slow down the video, but these match 100% what R produces. The test statistic for the interaction between fixture and layout, the two crossed factors, is 4.08. The F test for operator is 5.137. For the interaction between fixture and operator is 2.351. And then these next statements really just calculate the area in the tail from that F distribution. And I'm just going through them one at a time to show you that they are 100% equal to what R produces. So 19,383.02. And we're not really going through how to do this. You should always look at the interaction terms first before you look at the main effects. The purposes of this is just to show you how it's calculated behind the scenes. I'll probably have another channel where we apply all this stuff and we go through strategies of what you should and shouldn't calculate first and look at, etc. The p-value for fixture operator interaction is 0.036. It's the same. Okay, well, that's all I have for this video. Then the next little mini series within this is we're going to look at split plot designs, and then we'll probably stop because it's getting to be quite a big little playlist here. Hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.